Hello and welcome everybody to this Royal Meteorological Society Symons Gold Medal Lecture. The topic today is on missing gravity wave forces and scientific understanding, given by Professor Michael McIntyre. And Michael has kindly recorded his presentation today and joins us live for the Q&A. So we'll get to meet Michael later on. So I'm Liz Bentley and I'm Chief Executive at the Royal Meteorological Society. I have a few admin slides first to take you through before we get into the presentation. So we're on Zoom today. Some tips really for using Zoom if you're not familiar with it. We'll be using the Q&A today to take questions for Michael. If you look at the bottom of the Zoom screen, you'll see a little tab for Q&A. Please put your questions for Michael in the Q&A. You can do that during the presentation or during the Q&A session at the end. We have about 15 minutes for questions. You'll also notice that you can upvote a question. So if you like a question that somebody else has posted, if you click on the thumbs up sign underneath, then you'll see the number will start to increase, and that will prioritize the questions. And I'll try and get through as many questions as I can at the end of Michael's presentation. If you want to make the PowerPoint presentation a little bit bigger, then please close things like the chat just to enlarge the screen, make it as big as you possibly can, and then you'll see the presentation in full glory on your screen. And if you do have any technical problems at all, then I would encourage you just to leave the Zoom meeting and rejoin, and recommend using one of the browsers that you can see listed here. And finally, just to promote a couple of things with the Society. The first is our Met Matters. This is a content on weather and climate pitched at a general public audience. You can also sign up to a newsletter, so you'll get updates on content being loaded up on our Met Matters. So this is our general public kind of outreach activity of the Royal Meteorological Society. And finally, and I know many of you will be members of the Royal Meteorological Society, but if you aren't, please do take a look at our website. You can see the website link at the bottom of this slide to find out more about membership to the Royal Meteorological Society and the many different benefits of becoming a member. So I'm going to stop sharing my screen. And I'd like to introduce our Symons Gold Medal winner, obviously giving the lecture today, and that is Professor Michael McIntyre. And he was honoured with the Symons Gold Medal because of his outstanding contributions to our understanding of geophysical fluid dynamics. Michael's work on fluid dynamical wave breaking lies at the foundation of many classes of extreme weather events. His prescient insights and anticipation of the dynamics of breaking Rossby waves is at the heart of some of the most extreme bouts of severe weather in the world, including long-lived blocking events that cause intense cold outbreaks in winter and devastating heat waves and firestorms in summer. The impacts of Michael's work extend to tropical cyclones and even to other planets, such as the gas giants. Michael is an exceptionally inspiring scientist. His deep understanding combined with careful communication make his lectures and seminars an unparalleled experience. Numerous prominent researchers have profoundly benefited from Michael's mentorship and have gone on to hold leading academic positions worldwide. Michael's influence also extends to many other fields, including much cited work in musical acoustics, a breakthrough in solar physics, and a recent book entitled Science, Music and Mathematics, The Deepest Connections, which discusses biological evolution, human language, all of which demonstrate our unconscious mathematical abilities. Professor McIntyre is a giant in geosciences. His untiring communication of deep scientific ideas has armed generations of scientists with new tools, insights, and communication skills. And he's contributed to the amazing strength and vitality of meteorological research in the UK and beyond. And he's a worthy winner of this Symons Gold Medal. So we're now going to run Michael's presentation, which will last for about 45 minutes, and then we'll take questions. Thank you.
I was astonished and delighted to learn that I was to be honoured with the Symons Gold Medal and Lecture, though a bit unsure whether I really deserve it. It's meant to be for something called lifetime achievement, and well, looking back on my career, my first thought is how lucky I've been again and again, not least in having been able to focus on curiosity-driven research, much of it in collaboration with many wonderful postdocs and research students. It's the kind of research that resists bureaucratic constraints and tries to look at problems from more than one viewpoint, aiming at in-depth, multi-level understanding, which I'll discuss further, and which, by the way, is the kind of understanding that's still far beyond the reach of today's artificial intelligences. Well, I have quite a number of bees in my bonnet about these things, and will now proceed to let some of them buzz in this lecture. As the title suggests, this lecture is in two different parts. The first part is about an unresolved technical issue in weather and climate modelling, which I suspect may have dropped out of sight in the community, but which is still a significant challenge to our bright young dynamicists. It's the last problem I worked on myself a few years ago, and I did not get very far with it. And the second part broadens out to visit some generic issues about science itself and how best to understand it and communicate it. These generic issues have a philosophical flavour, but as a humble scientist, I think I'm allowed to discuss them in a simpler way than is permitted to a card-carrying philosopher. So here goes with the first part. So that's the title of my talk. I don't seem to be able to get the slides to move on. So we're going to have a little bit of a glitch in the recording now, in the hope that the motion of the slide is going to come back. Here we are. So that's the second slide. So continuing with the commentary. I show in my home address below because of isolation. That's my only postal address now, and you can check it out from looking at the web search below, which finds my home page and a note of this. What are these missing forces? They come from wave-vortex interactions. And if you recall that in standard parameterizations based on zonally symmetric mean flows, the wave-induced mean forces are made persistent with cumulative and therefore important effects by wave breaking or wave dissipation of some kind. Now, with wave-vortex interactions, the situation is fundamentally different because one can get persistent cumulative forces without any dissipation, and these forces are missing from the standard parameterizations. So I'm going to focus on a problem with interaction of waves by a vortex when the waves are not breaking or otherwise dissipating. And there are two non-trivial questions. One, where is the mean force exerted? And we'll see shortly that this illustrates what I like to call language as a conceptual minefield, because it sounds clear, but actually it isn't. We'll come back to that. Second question, when does the pseudo-momentum rule apply? Okay, roughly speaking, the rule says that we can pretend that pseudo-momentum is momentum. By the way, it's well known that I should just say that these two quantities are different. They belong to different translational invariance operations. Pseudo-momentum belongs to translation variance of the wave of the material medium in which the wave propagates, as distinct from momentum, which depends on translational invariance of the whole physics, independence of the origin of coordinates, if you will. And the rule, more precisely, says the following. This is the rule for waves in a material medium. First, you pretend that the waves have momentum given by the formula for pseudo momentum. This is only the simplest example. It's the pseudo momentum in a ray theoretic description with waves of energy density E and wave number K and intrinsic frequency omega hat. That's the frequency to an observer moving with the mean flow. Furthermore, you pretend that the material medium is absence, and you take the force to be equal to the rate of change of pseudo-momentum, either due to wave dissipation or wave generation in standard examples. There's a beautiful example of the second thing in Alan Plum's classic paper on the superrotation of Venus's stratosphere, where you generate pseudo-momentum using the solar tidal heating, and the effective force sends Venus's stratosphere into superrotation. And the rule often delivers the correct wave-induced mean force in many problems, especially problems with zonally symmetric mean flows. But if you consider the sort of problem I'm now talking about, a wave packet deflected by a vortex, as in this cartoon, we again have a non-zero rate of change of pseudo-momentum, now due to the wave refraction, because the refraction makes the wave number change as the waves go through. And the question is, does the rule still hold? And remember also, where is the mean force exerted, the mean recoil due to the wave refraction? Well, the simplest setting in which these questions can be studied is that of two-dimensional inviscid non-rotating fluid dynamics, either gas dynamics or shallow water dynamics, which mathematically are much the same thing apart from a certain parameter. What I did was to take a single wave train and a single vortex with a small core, and to get a tractable, soluble problem, I assumed that the Mach or Froude number is small. I call it epsilon. I assume that's small, which means I'm assuming wave refraction is weak. And the asymptotic regime is small wave amplitude, small weak refraction in that order. So here's a sketch of the setup. Outside the vortex core, this is the non-rotating problem. Outside the vortex core, we have a tangential velocity that's inversely proportional to radius. Later on, I'll consider a quasi-geostrophic version, rapidly rotating small Rossby number, and in that case, the tangential velocity comes out to be proportional to the first modified Bessel function, but more of that soon. Now, the first problem I consider is you take a wave train that goes past the vortex entirely outside it. This is a problem that I solved with my ex-student Oliver Buehler quite some time ago. We used ray theory, and we found that the pseudo-momentum rule is satisfied, but there's still a rather interesting result about where the mean force is exerted. Is it exerted where the waves are refracted? Well, that's what I mean by language as a conceptual minefield. That's an ambiguous question until you formulate it more precisely. Namely, if the waves were removed, then where must the force be exerted to have the same effect on the mean state? And the answer is, we thought, quite surprising. You must exert the force on the vortex core. We called it remote recoil because the waves refract in one location and the vortex here, and the vortex core is in another location remote from it. Okay, that sounds like something magical and mysterious until you look at how it actually works. Well, here's how it works. You have a wave train being refracted, as in this schematic, but you have a second order mean flow, second order in wave amplitude, mean flow, surrounding it like that, because the Stokes drift within the wave train varies across the refraction location, and it has to leak around on either side. But now look what that does to the vortex core. It advects it toward the left. And let's say at velocity u translation, and that changes the Kelvin impulse of the vortex, which is an appropriate measure of its, so to speak, momentum. And that rate of change is, we found, given by the pseudo-momentum rule. Just a few equations. I don't have time to really deal with this properly, but just to get a glimpse of what the mathematics look like. You have a two-dimensional vortex with a core vorticity, which I call omega naught. R is radial distance again. And the Kelvin impulse is defined as this rotated first moment of the vortex, of the core vorticity. And by the way, this depends on the origin of coordinates, but it doesn't matter because the rate of change of this, we find, does not depend on the origin of coordinates. So that's well defined. And the thought experiment involved here is to apply a suitably tailored body force field, I call it F, to the vortex core. And that makes the vortex move through the fluid with the same velocity if you choose the force field appropriately, like that. And the rate of change of Kelvin impulse is proportional to the total resultant force on the vortex core, as written here. And if you work that out, you find it's proportional to the Kelvin circulation of the vortex and the translation velocity. It's a sort of Magnus relation, if you remember things about spinning tennis balls and so on. Okay, that's essentially the main result here for problem 1. Now, problem 2 is a similar thing, except that we take a wave train that's infinitely wide and infinitely long. Now, there's a new effect in this problem, which you can read about in the theoretical physics literature. It's called the Aharonov-Bohm topological phase jump. And in this problem, you can see it in this far-field solution. Here are the wave crests in a far-field solution based on ray theory, and there's a phase jump behind the vortex. Of course, and that phase jump is proportional to the strength of the refraction, not surprisingly, according to this formula. Now, in a complete solution, that's smeared out. This is only ray theory, so really it's smeared out in a sort of wake region behind the vortex. Now look carefully, and you can see there's another effect, another refraction effect in this picture, which is actually the same effect as you have in problem 1. Namely, the wave crests are slightly rotated, as you can see if you look carefully, and that generally has importance comparable to that of the Aharonov-Bohm effect. We again find that the recoil is persistent and cumulative, again that it acts on the vortex core alone, and again that it satisfies the pseudo-momentum rule, at least at leading order for weak wave refraction. And this time, the recoil is made up of remote plus local contributions. Remote contributions, just like those in problem 1, and local contributions proportional to the Aharonov-Bohm effect. Now, I'll tell you a little bit about the quantum fluids literature because there are some strange things. In that literature, problem 2 has been studied because of the interest in phonon-vortex interaction. And the literature seems to recognize this local contribution. They call it the Jordansky force, governed solely by the Aharonov-Bohm phase jump. But the literature seems to ignore the remote contribution. It turns out that these local-only results are correct only in a special limiting case, in which the length of the wave train is taken to infinity first, and then the width of the wave train, and these limits are non-interchangeable. In all other cases, the wave crest rotations enter the calculation as well at leading order, and there are remote as well as local recoil contributions. Okay. So that's problem 2. I also studied a rapidly rotating version of problem 1. I'm going to call it problem 3 here. And in that problem, we have deep water waves going past a quasi-diastrophic shallow water vortex, and the asymptotics are even trickier. At the end, I'll give a reference to some papers for the technical, my published papers for the technical details. So I'm going to skate over a lot of these points here. What is this anti-Stokes flow? In a rapidly rotating frame, if you have deep water waves, if you have a uniform wave train, the Stokes flow is exactly cancelled by an equal and opposite mean flow induced by rotation, called the Searle anti-Stokes flow, after Fritz Searle, who first pointed it out. And you might think that would make the Brotherton flow and all the things I was talking about go away, but actually that's not what happens. When you have refraction, the anti-Stokes flow doesn't quite kill the Brotherton flow, and you still get remote recoil. And furthermore, in this problem, the pseudo-momentum rule survives as well. But, and this is interesting, the rule fails when the waves feel the bottom. If you make the wavelength a bit longer, so they're no longer deep water waves and they feel the bottom, the pseudo-momentum rule fails. And this adds to other known examples of rule failure associated with mean pressure forces on boundaries. These go back to the classical literature, such as Léon Brillouin's pioneering papers on radiation stress. And if you want to read about these things, a good place to start is Oliver Bühler's book on waves and mean flows, which I'll mention again. And as I say, in many of these problems, the problem is mean pressure effects on boundaries. In the present problem, it's pressure of the bottom boundary. And what happens is that the radiation stress field of the waves now has a sort of foothold on the bottom, and that breaks mean hydrostatic balance. So it breaks mean quasi-geostrophic dynamics. And I'm mentioning a paper here that says a bit more about this, although it's slightly to the side of what I'm saying. So just to summarize this part of the lecture, the main points, and they're all big challenges for young theoreticians. Firstly, the present results are confined to leading order in the weak refraction limit, the small Markov-Flood number, epsilon, and small Rossby number in the rapidly rotating case of problem 3. There are still open questions about the scope of the pseudo-momentum rule when the refraction is stronger. Another set of open questions: it's not known how to set up a conceptual framework that's general enough to support, for instance, parameterization via machine learning, which is obviously going to be important in the future. And to end with, just mention that my 2 published papers giving the technical details are available on my website. And if you web search for McIntyre, Aharonoff, Bohm, you'll get there in an instant and find reprints or preprints of those papers and detailed references. They came out a few years ago. Another paper worth mentioning is a more recent one by Oliver Buehler and a student of his that bears on the sort of fluid system that I'm using here for these examples, and also Buehler's book on waves and mean flows that I mentioned before. So now I'm going to shift gear and switch to the second part of the lecture. Okay. A wider perspective of generic issues in science. And I want to start by emphasizing the importance in science, or in any serious problem-solving activity, of multi-level thinking. That's to say, recognizing the simultaneous importance of different levels of description. And I want to just mention here that this point, recognizing different levels of description, is also important for many even wider issues of sociological and human significance. Conflating different levels of description causes confusion. For instance, in the debates about so-called consciousness and free will. And another example, sometimes rather distressing, is gender dysphoria, as for instance with trans women. These are individuals about whom you can say this individual is biologically a man, but mentally and socially a woman. And there's no contradiction because the two assertions belong to entirely different levels of description, vastly different levels. The biological levels, chromosomes and protein circuits, are far removed from the mental and social levels, with many layers of complexity in between. And if you're interested, I discuss all this in my book, but for now, I want to go back to generic issues in science. Now, another thing to say that's somewhat related is that taking more than one viewpoint is important. Why is this? Let me try to just state explicitly why all this is important. One example, though, of this is equations, pictures, words, and feelings, which I found in my own work to be most important. Work in dynamics of jet streams or mean circulations, you need to use equations, pictures, words, and feelings, and try to relate them to each other. So that gives you more than one viewpoint. So why are all these things important? Let me try and sort of summarize this. Multi-level thinking is important and complex at one level, because complex at one level could be simple at another. Also, complex for one viewpoint can be simple for another. And one of my favorite examples is the sharpening of jet streams, the great atmospheric jet streams and their ocean currents like the Gulf Stream keep themselves sharp with sharp velocity profiles and narrow velocity profiles. They keep themselves sharp over many thousands of kilometers of meandering. How does that work? Well, there's a viewpoint from which you can understand that very simply, and it's the viewpoint based on the quantity called potential vorticity, about which I've written a lot in the past. So I'll just mention it here. Another viewpoint is momentum transport, but it looks much more complicated from that viewpoint. And more generically, scientific progress has always depended on these things. And Newton's treatment of the Earth as a point mass illustrates both points. It's a particular point of view, it's a particular level of description, and it enabled Newton to work out the basic things about the dynamics of the Earth's orbit. Another reason why all this is important is that multi-level thinking is an antidote to extreme reductionism. That's the attitude in science, that the only useful way to look at a problem is to look at its kind of basic units, like atoms or electrons or genes. I think that for many years it impeded progress in biological evolution, where there was a mindset that only the gene's eye view is important, sometimes called selfish gene theory. I'll say a bit more about that shortly. But all this is needed for what I like to call in-depth understanding, which is outside the scope of even the cleverest AI, and I think it will remain so for many decades. Okay. So what is this thing called understanding? I want to view this from the perspective mainly of biological evolution. And the starting point is to say, well, it's bound up with the way perception works. If I perceive a charging rhinoceros coming at me, then I understand intuitively that I should jump out of the way. What could be more obvious? But all of this was and is central to survival in the past, and it still is central to us humans in this, almost everything we do, including the sciences, the arts, thinking skills, and, as I'll touch on again, communication skills. It's also central to how music works and mathematics. There's quite a lot about that in my book. A preview of which, by the way, you can find by going to the homepage using the web search phrase below. So the way perception works is central to all these things. What can we say about the way perception works? Here's my favorite starting point. Look at these 12 moving dots. This is a classic in experimental psychology. Anyone with normal vision who looks at these 12 moving dots, will see a person walking. And that's a very robust perceptual phenomenon that's been very well studied. What does this example tell us? It illustrates, for instance, that we all make unconscious assumptions. Here we unconsciously assume that the motion of the dots corresponds to a certain three-dimensional motion, the person walking, which is only one kind of motion that could give rise to the moving dot pattern. And that's completely unconscious. We have no choice but to see a person walking. Also, it shows we have unconscious mathematics, in this case, Euclidean geometry. Euclidean geometry, the mathematics of angles and distances. The brain must be using that to deduce the three-dimensional motion by fitting a mathematical model to the incoming visual data, all done unconsciously. And that's the basic point about how perception works. It fits models to data. And science, of course, does essentially the same thing. It fits models to data. So it's fundamentally an extension of ordinary perception. I would venture to think that that's a more important thing to understand about science than a lot of the things in all those books on the philosophy of science. But there you go. That's a simple and really, really basic point. And by the way, it shows that science is never about absolute truth. It's always about how good is the model, how widely applicable, how accurate, that kind of question. Another thing the walking dots illustrate is that we are perceptually sensitive to something that I like to call organic change. That means patterns. We're sensitive to patterns in which some things change continuously or by small amounts, while others stay invariant. And the invariant elements are always important. Now, I want to illustrate that point by turning to a different kind of word pattern, namely word patterns in written or spoken language. The same thing applies. Here's an example. Sentence, if you are serious, then I'll be serious. There's an invariant element, serious, and because of our perceptual sensitivity to organic change, it makes the sentence clearer and stronger than it would otherwise be. Some of us are taught in school that you shouldn't write a sentence like that. You should never repeat a word. In place of the second word, serious, you should put another word like, well, if you are serious, then I'll be earnest, or I'll be also. And that, I contend, weakens the sentence. And in the case of I'll be earnest, makes it pretty unclear. And all the languages I've looked at work the same way. Here's an example in Chinese. This is a rough translation of that sentence. And even though I don't know any of the Chinese languages, I can see that these two parts of the sentence have an invariant element, and my Chinese colleagues assure me that that sentence is clearer and stronger than the variant on it that I've described. Okay, so that's touching on something that's important for communication skills, simply appreciating the importance of our sensitivity to organic change and its invariant elements. So here's a sort of attempt to summarize where we've got to and expand slightly. Science and ordinary perception both work by fitting models to data. Unconscious assumptions are involved. We all have unconscious mathematics. And by the way, I gave the example of Euclidean geometry, but here's another example, which is another classic in experimental psychology. If you stare at the inner edges of these black line segments here, everyone with normal vision sees a beautifully smooth curve joining them. That curve is the solution to what mathematicians call a problem in the calculus of variations. You consider all the curves that can join the ends of the black segments, and you pick out the curve that is smoothest in some suitable sense. That's a volume in the calculus of problem in the calculus of variations. And by the way, calculus of variations is important in theoretical physics, as I further discuss in my book. So all these things go into our unconscious mathematical models that mediate perception and understanding. Furthermore, science and ordinary perception use varieties and hierarchies of models simultaneously. That's again returning to this theme of different levels of description, different viewing angles. An example of this is how our brain hemispheres work. One of them has a repertoire of models that are sort of dissected, that go into fine detail, focus on fine detail. The other uses models that are more holistic, fuzzier, but more aware, for instance, of overall spatial relations. And in most people, these are the left and right hemisphere respectively, but sometimes it's the other way round. So that's just making the point that varieties and hierarchies of models and more than one level and more than one viewing angle are sort of natural and built in by evolution, built into our brains as they've evolved. And similarly, science needs such a hierarchy of models that are both precise for some purposes and fuzzier and more intuitive. And scientific understanding perception is deepened, as I said before, by looking at a problem from more than one viewpoint and using more than one level of description. By the way, James Black's wonderful book on the great physicist Richard Feynman has some beautiful examples of Feynman using all of this in his scientific research on fundamental physics. Now, my last point in this lecture is the obvious point that unconscious assumptions can, of course, be wrong. And I want to end with 3 examples of wrong unconscious assumptions. Indeed, all 3 can be seen as obviously silly once they're made conscious. And I hope many of you might recognize at least 2 of them because they come from my field of atmospheric dynamics. The 3rd example is from biology, biological evolution, to be precise. And it, I argue, has greatly impeded progress in the past in understanding our own human nature, as well as biological evolution in general. I should add that the cutting edge of the field now recognizes a lot of this. Okay, so assumption one is small implies unimportant, which, by the way, tended to be get tangled up with the old energy budget mindset, saying that if you want to understand atmospheric circulations, the way to do it is to consider the energy budgets. But of course, that distracted attention from small effect, because you tended to look at the largest numbers about energy flows. Of course, it's easy to think of counterexamples. I'm going to give three: an audio amplifier, very obvious, the ozone hole, and the climate system. So here we have input signals on the left, internal variables in the middle, and output signals on the right. In an audio amplifier, of course, you inject a few electrons as a small input current that gives rise to large internal flows and to large output signals. For the ozone layer, for its chemistry, you inject small amounts of chlorofluorocarbon molecules, and you get large flows between the chemical species, including a large destruction of ozone, converting it to O2. And that's a catalytic process, so that a single CFC molecule can be responsible for destroying thousands of ozone molecules. So that's a relatively large output signal. And finally, as people are very well aware of these days, is the climate system, which has various small inputs. One of them is injecting carbon dioxide molecules. Another one is changing the Earth's orbit slightly. So that's a small input that we know was extremely important in the past for the big climate changes of the past million years or so. So these small inputs give rise to large internal flows of water vapor and therefore energy and so on and so forth. So you have, in effect, a large output signal from that. And by the way, the current input from injecting CO2 is not really a small input by any natural measure, because the natural range of variation of atmospheric CO2 is something like 100 parts per million by volume. And today we bump that up to well over 400 parts per million. So it's an amplifier, but it's being given a rather large input. So it's no surprise that we are now seeing large climate changes and even larger weather extremes. So that's assumption one. Assumption two, wrong assumption two, sometimes unconscious. Correlation implies causality. Well, it's well appreciated now that that can be wrong, but its mathematical version, I sometimes still encounter. I call it the A equals B assumption. If you're playing with a mathematical model and you have an equation A equals B, okay, all that means is that A and B are perfectly correlated. It doesn't mean that B causes A or B drives A, as is sometimes unconsciously assumed. And I think part of that is because it looks like a line of computer code in which you could say that B causes A. I don't really have time to talk about counterexamples in atmospheric circulation, but here's a very simple one. If you push a dinner plate across along a table, you have an equation like this. If you push it slowly, you have a pretty good balance between minus the friction force, B, and the applied force, A. But just writing B on the right-hand side doesn't mean that the friction force drives the motion of the plate. Let me just briefly mention the circulation example. For large-scale circulation in the stratosphere, the so-called Brewer-Dobson circulation, you used to read quite often it's driven by heating, net heating, including solar heating. But that's wrong in the same way as saying that the plate is moved by the friction force. Actually, the heating is part of the response to other things, and such as wave-induced forces. Okay. My third example is what I call the multi-timescale fallacy, saying that dynamical mechanisms having disparate timescales cannot interact strongly. And in the biological literature on biological evolution, you read, especially a few decades ago, you read a lot about what they call ultimate versus proximate causation, which is only a fancy way of talking about slow processes and fast processes. Slow processes such as genomic evolution and fast processes such as the development of a single organism, and it's assumed that the two don't interact. And that's a fallacy as well. And that, by the way, is well recognized in the recent literature, but for a long time it impeded understanding of biological evolution. Of course, you can think of much simpler counterexamples, which is easy for anyone who knows any physics. One of them, the simplest I can think of, is gas pressure, where you have a fast process, a short timescale process, molecular collisions interacting with slow processes with long timescales, such as changes in gas pressure and temperature, as when you pump up your bicycle tires. And that's not only a significant, but also a crucial interaction. There's a zero order, leading order interplay between the fast and the slow processes. So it's complete nonsense to say that disparate timescales say they don't interact. Wave mean interaction, as in gravity wave parameterization, that's another example, because the waves can be effective even when their timescale is very short compared with that of the mean flow changes. And in biological evolution, as I sort of said already, the fallacy, the unconscious assumption has impeded understanding of evolution in general, and in particular, the evolution of our pre-human ancestors. And there's more about that in my book, so I'm going to leave you with the thought that all this reminds us why multi-level thinking and multiple viewpoints are so important, and how this impacts on communication skills, appreciating the importance of organic change in word patterns, for example. And of course, communication skills are important today, not only for public understanding, but also across all the scientific disciplines with their multifarious specialities. And all of it turns on how perception works. And I hope I've helped to make that last point scientifically interesting. Thank you very much for listening.
Great. Thank you very much, Michael, for recording that lecture. Very thought-provoking lecture. And Michael, if you'd like to put on your camera, put mine on too. As I mentioned at the beginning, you're here live to join us for the Q&A. Welcome. So we're now moving into questions and answers. If you have any questions for Michael, either on his presentation or anything really, we've got the opportunity to have a conversation, I guess, with Michael. Please do put it in the Q&A and I'll get to as many questions as I can.
Can I say something immediately?
Yes, please do.
My Zoom system has been playing up and it keeps throwing me off. And luckily I've managed to get back on about 3 times, but obviously it might happen again and I'm not sure how to manage that.
I noticed during the presentation, Michael, that you had dropped in and out. So we'll try and push on, hoping that you will stay with us. If we do drop out, then I think what we'll do is take the questions from the Q&A and try and respond to them in slower time. But let's push on with the Q&A. We have you here.
Yep.
I have a question from Tim Palmer, but he would rather ask it. So I'm just wanting to know, Kat, can we bring Tim up to the stage? Here we are. There we go, Tim. So if you want to unmute, the floor is yours.
Okay. Am I unmuted?
You are. Yes, we can hear you, Tim.
Okay, fantastic. Well, I'd like to just start by congratulating Michael on the Symons gold medal. Michael, can you hear me?
Yes.
Yes, fantastic. Um, I owe a lot to Michael's guidance and mentorship in my own career. I had many happy and insightful times visiting him in Cambridge and learning about wave mean interaction. And I want to thank Michael for all of that. The question I wanted to ask is a little bit of a general one, but it's motivated by the first part of your talk on the potential for including wave refraction processes as parameterized processes within models. And the issue I want to ask you, Michael, is that I fear that over the years, the sort of GFD techniques that you have both used and pioneered are becoming more and more niche in the weather and climate community. And I suspect many of today's weather and climate scientists who use models probably don't have the mathematical techniques and knowledge to be able to actually work on these parameterizations. In a sense, what I'm saying is that GFD seems to have become a much less, let's say, commonplace research tool in the weather and climate community than maybe it was, 30 or 40 years ago. To some extent, this is because, model data has become very freely available and it's easy to do diagnostics on model data. Things have actually taken even a step, perhaps in the even worse direction, in that the growth of AI has started to mean whether we need to bother understanding anything at all about the laws of physics, and we just allow the AI to, as it were, learn Navier-Stokes and whatever else it needs by its own. So I just wondered if you'd like to kind of comment on these perhaps trends in our sort of education system, and whether we should take stock of where we are now and think about whether we need to retool a little bit in our tool set. So I'll leave that with you to speculate on or to say what you think.
Well, thank you, Tim. You've raised an enormous set of issues which overlap with some of what I was talking about, of course, because what AI at present promises is not multi-level, multi-viewpoint understanding, but understanding from its viewpoint, which at present is much, much narrower. And I don't think AI has the ability to look at things from many different angles and appreciate how they might be connected. Of course, the research efforts going on now must be focused on trying to use AI well, and therefore that takes effort away from the sort of thing I used to work on and in trying to understand wave vortex interactions. And really, I'm not sure what to recommend. I left it as a challenge for young theoreticians. I hoped, as I said at the end of the first part of my talk, that there will be some young theoreticians who are going to have to be very smart and very versatile in their thinking, who can pick up on this sort of point and try to understand a bit of what I was talking about, and also how to perhaps bring that into a more AI-driven data study, which of course is going to have to involve doing experiments, doing systematic experiments, changing things systematically and seeing the effects is a terribly important part of acquiring multi-level understanding. I'm not sure I can say much more that's useful.
Thank you.
Thank you, Michael. And thanks for the question, Tim. I'm going to go to the Q&A now. So we have a question referring to the first half of your presentation, Michael, from Adam Scaife. First of all, Adam says, it was a pleasure to see you win this well-deserved award. And the question is, can you tell us about the wave recoil force? How does it compare in magnitude with parameterized forces that we already include in numerical models, not least via your work with Chris Warner, for example? So is it of comparable magnitude?
Broadly speaking, yes, I would say. There hasn't been much work on quantifying that, so it's difficult to say more. But the standard parameterizations deal with gravity waves being substantially refracted. And intuitively, I would think that the refraction due to wave vortex interactions in the real atmosphere is of a similar order of magnitude, because that refraction is obviously important. I'm not sure I could say much more that would preempt serious work on that.
Thank you. Adam has responded back to that with, in that case, blimey, exclamation mark. So I guess that's a surprise that it is of a similar magnitude.
I could mention perhaps that my ex-student Oliver Buehler, whose lovely book on waves and mean flows I mentioned before, as basic to all this. Oliver and one of his students, Alex Hasher, tried to have a go at this problem about 10 years ago, I think, but I don't think they've done much more on it. So it's a lot of open questions.
Great. So question, I think, relating to the second half of your talk from C. Lamb. What do you mean by making people understand a particular subject when they don't have any idea about the equations involved? This is a common problem encountered when we speak to the general public. So do we show them pictures or photos to give them a different kind of understanding, in quotes?
Well, that's the problem of being a skillful popular science communicator. What can I say? Well, I try to do this in my book, a preview of which you can see on my website. I tried to talk about the significant issues without putting in any equations. In other words, using words and pictures, mostly words, to talk around the issues. I mean, you can do things like say what mathematics is. It's a way of it's a way of describing a situation in a completely self-consistent way. Any situation that involves amounts of quantities, such as the magnitude of a force. And it's impossible to say much more in a minute or two. So if you're interested in that, I really do recommend you have a look at my book.
Right, thank you. So just thinking, I mean, obviously with multi-level thinking and unconscious assumptions, it is an argument for having much more diverse groups of people working together on these challenging problems. So everybody can bring a different perspective to it. And that, I mean, I think it is a good argument for diversity, isn't it? And you know, having as diverse a group of people working on these problems, would you say, Michael?
Yes, absolutely. And of course, that is also why communication skills are important, and which is why I talked about how basic it is to recognize our perceptual sensitivity to organic change. I didn't quite say why the walking lights showed that, but of course, there are things changing and there are things staying the same. Remember, organic change, we're sensitive to patterns in which some things change continuously or by small amounts, and others stay invariant. And in the walking lights, the things that stay invariant are not only the number of dots, but also the distances between the dots in the three-dimensional space of the model that the brain fits. So that's how that illustrates organic change. And then I went to word patterns, where respecting organic change allows you to write and speak more clearly. And that's kind of basic to all this. And I would encourage any young people to take that on board.
And I think that's a lovely place to end here. You know, you've left us with that challenge, and I think it's really important for all of us to think about how we, you know, we don't make these unconscious assumptions, that we think as widely as possible, both in the science that we do, but how we communicate it. So it just leaves me to say a huge thank you to you, Michael, for well, congratulations on winning the Symons Gold Medal, but for giving us such a thought-provoking lecture today. I'm really grateful for you. Thank you very much.
Thank you for having me.